So today we're going to go over angular displacement and velocity. We're going to look at the basics of circular motion. Hopefully you've had a chance to watch this video. How fast are you moving right now? It will give you an idea of just how we take things for granted, how we feel that we're standing still, but in fact we're moving at some incredibly high velocities. And in fact, what we'll do at the end of this section is go back and revisit some of these ideas by doing some calculations to work out exactly how fast we're going, but that's later. So what we're going to do today is look at the difference between, or convert between, degrees and radians. We're going to revisit the definition of a circle in order to then describe circular motion. We're going to express angular displacement in terms of radians. So first I'll define angular displacement, and then we'll look at how to quantify it using radians. Then we're going to be looking at the terms angular velocity and differentiate it from linear velocity. Linear velocity is what you were using in topic 2 to describe motion. So we're going to introduce a new idea and do a comparison. And then we're going to recall and apply the expressions for angular velocity. We're going to look at some relationships so that we can do some calculations. So let's describe motion in a circle. How do we describe it? Well, first we're going to start with the definition of a radian. We're going to look at how to measure and quantify a circle using radians. By definition, a radian is a section of a circle. It's a piece of a circle. And how do we define how much of a circle it is using the radius. If you take the radius length and apply it to the circumference to cut out an arc length, then what you do is you end up fractioning out a piece of a circle. So when this distance here is equal to a radius, the entire section here is a radian. So the angle in radians is defined as the arc length divided by the radius. Looks a little bit like this. Just show you this. If we take a radius, take that length and apply it to the circumference, that entire piece is 1 radian. If we continue cutting up the circle into these radians, we can see some really neat combinations. 3.14 radians is half a circle, or actually, to be more accurate, pi, 3.14, etc. And then 2 pi is an entire circle. But let's have a look at that 2 pi in more detail. So what we can do is define the number of radians, right? So this theta would be a number of radians. How many radians, right? Would be the ratio of this arc length, right, divided by the radius. Thank you, very loud motorbike. Now, 1 radian would be equal to an arc length of r, right? So the arc length r divided by r would give us 1 radian. So now have a look at an entire circle. What is the relevant arc length for an entire circle? It would be the circumference. The circumference is equal to 2 pi r. This distance, this entire distance. So our arc length for an entire circle would be 2 pi r, and the radius would be r. So the number of radians in an entire circle would be 2 pi r divided by r, which leaves 2 pi radians. And that's in fact the definition of a circle in terms of radians. This gives us a really good starting point to then define any other fraction of a circle. Always starting with 2 pi as an entire circle. Okay, so we can have a look at 90 degrees, pi over 2, 180, pi, 360, 2 pi. And then 45 degrees, if we think about 90 as being pi over 2, half of that would be pi over 4. Okay, so is that clear? I hope so. Have a look at these diagrams and make sure that they make sense. Pause the video if necessary. Now, just to cement our learning, this is more of a pure maths skill, but let's have a look at how do we convert. If we need to convert from degrees to radians, then it's fairly straightforward. 360 degrees equals 2 pi. So you can multiply by 2 pi and divide by 360. Similarly, if you're converting from radians to degrees, you would multiply by 360 and divide by 2 pi. Have a go at these 4 questions. See if you can get the right answer. I hope you got the right answers and are ready to move on. If not, maybe take a step back and have a look at the explanations again. So we're now going to look at some quantities. We're going to look at motion quantities, what an object is doing when it's moving in a circle. The first quantity that we must define is angular displacement. Angular displacement, expressed as the theta, is an angle in radians. It's not a distance in meters. We're not looking at how much distance we cover. We're actually looking at the angle we're sweeping out along here. So that's angular displacement, always in radians. Have a look at this question. Calculate the angular displacement subtended by the hour hand on the clock after a time period of 2 hours. What is the angular displacement covered at that time? Hopefully you got that right. It's 0.33 pi radians. So that's how we refer to as angular displacement. The next quantity is actually something you've come across before. It's referred to as the linear or sometimes tangential velocity. It's very similar to what we come across before. In fact, it's exactly the same as distance over time, right? Speed. It refers to the actual distance in meters that you are covering as you move round in a circle. As you know, the total distance that you cover as you move round in a circle is 2 pi r, the circumference. And the time in that case would be the time taken for one revolution. The actual name for that specific time is called period. We came across that in waves and it's interchangeable. So V would be 2 pi r, the circumference, divided by the period. V being the linear velocity of the point on a rotating object. Now, the linear velocity of an object very much depends on those two quantities. The circumference, the total distance that has to be covered, and the time that takes to do that. Now, as you can see, 2 points on a circle at different distances from the center will have a very, very different velocity. If you look at this example, you can see that the blue arrow represents an object that needs to travel a much bigger distance than the red, or the object the red dot represents. So therefore, this object will have a much higher velocity. You can see how that's represented here. All of them have a velocity that's represented by 2 pi RT. But in this particular case, the yellow and the red dots, they have a much lower circumference. And so therefore their velocities are sequentially less and less. Red having a much lower velocity. So that's velocity, linear velocity. Angular velocity is the same idea, but this time considering that angular displacement. Angular displacement over time gives us what we call angular velocity, sometimes referred to as angular speed, but it's the same thing. The angular speed or velocity, omega, is equal to the angle that's swept out in radians over time. And that would be equal to, for an entire circle, 2 pi, which is one entire cycle, divided by the period. The units of angular velocity are radians per second. Radians s to the minus 1. Now, as you can see from this diagram, the angle that swept out, using exactly the same example as before, the angle that swept out by the red and the blue is the same per unit time. So therefore there is no change in angular velocity as you change this position from the center. Now this is very different to linear velocity. Okay, and this is a diagram kind of representing the difference between the two. The angular speed represents the displacement, the angular displacement over time, and the linear speed is directly specific to the circumference, right? It's the total distance covered. I hope that makes sense. Okay, we're going to look at this last thing, which is how do we connect those two quantities together? How do we put linear and angular velocity together? Well, the relationship that brings both of those quantities together is v, linear velocity, equal to angular velocity times the radius. Now, see if you can come up with that equation. See if you can derive this equation on your own. Have a think. Get a piece of paper, back of an envelope, see if you can figure it out. And if we look at the relationships that we had already, we had angular velocity is theta, the angle in radians, over t, and velocity was 2 pi r over t. Take this first relationship and we substitute the idea that a full circle would be 2 pi and t would be equal to the period, capital T, then what we'd end up with is 2 pi over capital T. 2 pi over capital T then becomes omega. So all of this is the same as the angular velocity, omega, leaving the previous equation, which is this one. V equals 2 pi over T r. Okay, I hope these ideas are clear. I'll give you some questions now to try and help you cement your knowledge.